Any doubt is there in the question paper? Otherwise, I will start this week's syllabus, some capacitors, last topics. My students.
Sir, we didn't get the paper yet, sir.
Why? It is not post. Oh. Can I post this one?
Yes, sir.
Yes, sir.
I will call the in charge and this is a Super 60 batch 2 one, incoming senior.
Yes, sir.
Okay. Okay, ma'am. Is it coming?
Yes, sir.
No. If you have any doubts, ask me. Don't waste time. My students, all of you unmute your microphone. If you have any disturbance only, you mute your microphone. Otherwise, you kept it in unmute.
Sir, question 125.
Question number 125. Just a minute. One 125. A parallel plate condenser has a uniform electric field in the space between the plates. If the distance between the plates is d and area is a, the energy stored in the capacitor U is equal to half C square, no? C is equal to epsilon naught A by D. V is equal to E into D whole square. Since E is equal to V by D. This is the relation between electric field and electric potential.
Yes, sir.
So that can written as half into epsilon naught A by D into E square D square. So here this D gets cancelled with each other. So this is equal to half epsilon naught E square A into D. That is the answer. Already I gave this one in our notes. Half epsilon naught E square AD. Third option. Here AD is known as volume. This is known as energy density. No. AD is equal to half epsilon naught E square. I gave this one also. This is known as energy. This is known as energy density. Energy stored per unit volume. Okay, ma?
Yes, sir.
Next. Here 124 actual out of service sum. 124 force between the plates. Today we will discuss after this question paper. And
Sir, 130.
130,
1.
131. Equivalent capacitor. Here that diagram can be drawn like this. This is one capacitor. These are the two capacitors are connected like this. And these are the two capacitors connected. Here in between, this is, let us say, B. This is A. Conveniently, one should draw like this. This is 4 microfarad. This is 4. This is 4. This is 4. This is 4. These two are in series now. This can be written as 4 into 4 by 4 plus 4. 16 by 8. 2 microfarads. This also like this 2 microfarad. This is 4 microfarad. So here this can be written as drawn like this. Like this. This is B, this is A. So this is 2, this is 4, this is 2. Therefore, CAB is equal to all are parallel. 2 plus 4 plus 2 is equal to 8 microfarads. First option. When potential difference is applied, same charge flows. Here charge divides like this. This charge flows on this and comes through here. That's why these two are said to be in series. Here charge divides into 3 parts. That's why these are in parallel. Here the charge flows through them also same. That's why these two are in series. If charge divides parallel, if same charge flows on the plates of the capacitors, then they are connected, said to be connected in series. Okay, next. students,
No,
ask it. Shall I rub this one? Verse 144. Here, a battery is connected across the two capacitors like this. This is C and this is C by 2. This is C by 2. Then what is the work done on that? Here, answer is wrong in our material also. Here, same some done in our class. But key is there, key wrong is there given. Wrong key is given in our book. Here, C equivalent is equal to how much? C plus C by 2 is equal to 3C by 2. Therefore, the work done in charging fully both the condensers. So that is the question. So work done is equal to half into C equivalent to EV square. So half into C equivalent is equal to 3C by 2 into V square. So answer is 3 by 4 CV square. Here in textbook, half CV square given. Next, students.
That's it, sir.
Come on. Now which question? One 40 and 124 out of syllabus. Actually, this week syllabus. That one. Force between the plates. Okay, now. Shall I start this week syllabus? Yes,
sir. Yes, sir.
Okay, doubts and level kada?
No, sir.
Okay. Here in this week we have force between plates of parallel plate capacitor charged capacitor and Van de Graaff generate from to this chapter, and then current electricity up to some extent. That is this week's syllabus. So now let us discuss about force between the plates of a parallel plate capacitor. Note on the side heading. Force between the plates of a charged parallel plate capacitor. Here let us consider a parallel plate capacitor like this. Here this is a charged plus Q, this is a minus Q. Due to the unlike polarity of charge, the attractive force is acting on this. That is, let us say, F force on second plate due to first plate. Similarly, there exists a force on first plate due to second also, known as mutual force of attraction. Due to this, let us say, this plate moves to this position, new position. This is the new position of the plate. So that this distance is a small dx, and the distance between the plates is now x. This is the diagram. Due to this force of attraction, just it displaces by a small distance dx, let us say. Okay, draw the diagram. In new position, what is the energy stored? Come on. Energy stored
half epsilon naught E square
as
delta.
general formula, right? How epsilon naught E square AD, no, like 8 instead of D, we use X. Energy stored in the capacitor U is equal to half epsilon naught E square A into X. Here X is the distance between the plates. Okay, now differentiate this with respect to X. Du by dx is equal to how much? Half of epsilon naught d by dx of X. What is the d of X with respect to X? 1, right? So this can be written as half epsilon naught. Fine. Since force F is conservative force field. Conservative force field. F can be written as minus du by dx. No. Relation between potential energy and force, conservative force. In work power energy, the first theorem, we use this relation. F is equal to conservative force is defined only for potential energy, or potential energy is defined only for conservative forces only. There is no kinetic energy in such cases, where negative sign indicates that attractive force. That's all. Okay, this implies F is equal to minus half epsilon naught E square into A. E square into A, where negative sign indicates that force is attractive. Force is attractive. Therefore, mutual force of attraction mutual force of attraction between the plates is given by F is equal to half epsilon naught E square A. This is the final formula without negative sign. This is actual formula. This is the force of attraction. Why? Because negative sign indicates the force of attraction. That's why the mutual force of attraction and then force due to first plate on second plate, force due to second plate on first plate is given by half epsilon naught E square A, where A is common area of each plate. If a smaller plate and bigger plate, two different plates are given, we use A as the area of a smaller plate, not bigger plate. That's why it is known as common area between the plates. Is it clear?
Yes, sir.
Completed, huh?
Yes, sir.
Now here, two cases are arranged. If a constant charge is present on the plates, if constant potential is present on it. That means after charging, battery is disconnected, isolated capacitor and down. If the capacitor is isolated means battery is disconnected after charging. If the distance between the plates changes, then how force change? That is important. Similarly, without disconnecting the battery, how force between the plates changes when the distance between the plates changes. These two cases are important. Shall I rub this one?
Yes.
Yes, sir.
Okay. Case 1. If the capacitor is isolated, that is, after charging, battery is disconnected, then Q is constant. Charge on the plates is constant. Q is Q on plates. Constant. Therefore, electric field between the plates E is equal to sigma by epsilon naught is equal to Q by epsilon naught A. Therefore, its mutual force of attraction is equal to half into epsilon naught into Q by epsilon naught A square into A. This can be written as half into epsilon naught into Q square by epsilon naught square A square into A. This square cancel, this epsilon naught, this square cancel. This implies F is equal to Q square by 2 epsilon naught A, which is independent of distance between the plates. So a constant value of force is required to separate, to increase the separation, to change the separation between the plates. To change the separation between the plates. Increases or decreases, whatever it may be. That is case 1 number. If battery is disconnected, charge on the plates Q should be the same. Okay, whatever it may be, distance between the plates decreases or distance between them increases, constant force is required. There is no variation in the force. Is it completed?
Yes, sir.
Next one, case 2. If potential difference V between the plates is constant, that is, charging battery is not disconnected, charging battery is not disconnected, then E is equal to V by dm, where D is distance between the plates. Therefore, force F is equal to half epsilon naught V by D whole square into A. Instead of E, we write E by V by dm. So this implies F is equal to half epsilon naught V square by D square into A. This is the formula. This implies F is directly proportional to 1 by D square. Therefore, in this case, variable force is required. In this case, variable force is required to change the separation between the plates. Variable force is required to change the separation between the plates. Why? Because F depends upon distance. F is directly proportional to D square. If D increases, force on the plates decreases. Is it clear?
Yes.
All of you noted?
Yes.
Now, let us discuss about the Van de Graaff generator, last topic in this lesson. Note down this heading. Van de Graaff. Van de Graaff generator. This is scientist name of Van de Graaff. What is a Van de Graaff generator? Do you know anyone? Here, Van de Graaff generator is the electronic device which is used to produce high potentials, so that very strong electric fields. Okay, under laboratory conditions, if we want to produce high potentials or high strong electric fields, we use this instrument known as Van de Graaff generator. Okay, so it is a device which is used to produce high voltages in the order of millions of volts. Million, in the order of millions means, million means 10 lakhs, 10 power 4 volts. 5 into 10 power 4, 10 into 10 power 4, 8 into 10 power 4, like that. In the order of millions, that means in the order of 10 power 4 volts. In general, the production of such high voltages is not possible under practical conditions. Under laboratory conditions only we can produce such high voltages. That instrument is known as a Van de Graaff generator. Here this works on a principle that if any two concentric shells are considered, charged shells are considered, and inner shell and outer shell are connected by a wire, then irrespective of potentials between them, the charge on the inner shell completely flows onto the outer shell. That is the principle. Here in general, we know that charge always flows from high potential to low potential. But here in this principle, we can show that charge flows from low potential to high potential also. If two charged concentric shells are considered and they are connected by a conducting wire. That is very important. Even though the potential of inner shell is less, if inner shell and outer shells are connected by a wire, then charge flows from inner shell to outer shell. That is the principle of Van de Graaff generator. And we can prove that principle also. Is it clear?
Yes.
Yes.
Okay, Van de Graaff generator. It is used to develop very high charges and strong electric fields that is very high voltages in the order of 10 power 4 volts. Principle. Here, this is a capacitor, this is a capacitor. This is a concentric. Here, inner may be conducting shell, or sphere, solid sphere, conducting sphere. This is a conducting shell. Okay, the charge on this is equal to, let us say, Q2. The charge on this is equal to Q2. The charge on this is equal to Q1. Let us say its radius is equal to R1. Its radius is equal to R2. This is center, concentric center. Inner should be shell or sphere, solid sphere, but outer should be the shell. Here, if this inner shell and outer shell are connected by a conductor, conducting wire, then this charge total flows onto this Q1 plus Q2. There is no charge on the inner shell, 0. This is R1. This is R2. That is the principle. Irrespective of potential of this, or irrespective of charge on the outer shell. Okay, actually, the charge present on the shell already present on it opposes the further flow of charge on it actually. But here, in such cases, if this is concentric and these are conductors, they are connected by a wire, conducting wire, then the charge on the inner shell, irrespective of its potential, even though it has a low potential, charge flows from low potential inner shell to high potential outer shell. That is the generator principle. This is also called a generator principle, Van de Graaff generator principle. It states that when a charged inner shell or sphere inner conducting, charged conducting inner shell or sphere is connected by a conducting wire with the concentric outer conducting shell. It may be charged or uncharged, whatever it may be. Then the total charge on inner shell flows onto the outer shell. That is the principle. Is it clear or any doubt? Students?
No doubt, sir.
Okay.
No doubt.
Now let us prove this principle. All of you completed? initial potential of the system is, what is the potential of this system now? Tell me. Charge Q1 is on the inner shell, charge Q2 is on the outer shell. Initial potential of the system. V1 is equal to how much? What is the potential of this? Potential of a shell, charged shell. 1 by 4 pi epsilon naught into Q1 by R1 plus 1 by 4 pi epsilon naught into Q2 by R2. This shell is 1 by 4 pi epsilon naught into Q1 by R. Due to this is equal to 1 by 4 pi epsilon naught into Q2 by R2. So total the potential is, it is a scalar quantity. That's why we should add both. Next, final potential after connection of the system is, at the first number, let us say V2. If there is no charge on this, but total charge flows onto this. That's why 1 by 4 pi epsilon naught into Q1 plus Q2 by, we use either R2 or R1. Tell me anyone?
R2, sir.
R2, right, very good. If there is no charge on R1, no. That's why we use R2. This is equation number 1, this is equation number 2. Therefore, what is the potential difference? Therefore, potential difference between initial and final states of the system. Potential difference V1 minus V2 is equal to 1 by 4 pi epsilon naught into Q1 by R1 plus Q2 by R2 minus 1 by 4 pi epsilon naught into Q1 plus Q2 by R2. This implies V1 minus V2 is equal to how much now? Expanding on expansion, we get 1 by 4 pi epsilon naught into Q1 by R1 plus 1 by 4 pi epsilon naught into Q2 by R2 minus 1 by 4 pi epsilon naught into Q1 by R2 minus 1 by 4 pi epsilon naught into Q2 by R2. So this term gets cancelled with each other. This implies V1 minus V2 is equal to 1 by 4 pi epsilon naught. Here is Q1, here also Q1 is there. That's why Q1 also taken common. Q1 by 4 pi epsilon naught into here 1 by R1 minus 1 by R2. This is the potential difference according to generator principle. Important and multi problems, it is useful. So here the potential difference between the shells depends upon the charge on the inner shell only. It is independent of charge on outer shell. That's why irrespective of charges on the shells, when they are connected, total charge flows onto the outer shell only. That is the meaning of this equation. Is it clear?
Yes, sir.
It means difference. It remains the same. It remains the same for any value of Q2. For any value of Q2. Irrespective of charge already present on the outer shell. If inner shell and outer shell are connected, then the total charge on the inner shell flows onto the outer shell. So that the potential difference attained is like this. So, two concentric charged shells are connected, then all the charge resides on the surface of on the surface of outer shell, spherical shell. This is about proof of Van de Graaff generator. If we supply charge to the inner shell, then that charge supplied to the inner shell continuously flows onto the outer shell when they are connected, irrespective of the potentials. Okay, but that's why the potential of outer shell is very, very high. So we can increase the potential of outer shell in the order of 10 power 4 volts, some millions of volts and down going on supplying the charge to the inner shell, and is it connected to the outer shell, then charge going on flows onto the outer shell, even though the charge on the outer shell is some millions of volts, and hence it produces a high or strong electric fields. Am I clear now?
Yes, sir.
Okay. Now here, what is the construction and working of this Van de Graaff generator? It has a, for theory only we draw that diagram of inner sphere and outer shell. But practically under laboratory conditions, that arrangement is not possible. So here under laboratory conditions, the construction and working of Van de Graaff generator is like this. Construction and working. Principle, theory, construction and working. Here it has a big sphere like this. At lower end, it is connected to insulating stand like this. This is insulating stand. Okay, this is kept on the ground like this. This is the ground. Here it has a wheel like this. Pulley. Here a belt is attached to another pulley arranged at the bottom of this arrangement. It has inner pulley also like this. This is a motor. It has inner pulley. It is connected by another belt like this. It is connected to the earth. It is not connected to the earth. This is the motor. Here, this is the belt, insulating belt. Here, a brush is arranged like this. This is a brush arranged like this. Here also, a brush is arranged to this belt, so that the charge flows onto the belt like this. This is another brush. It is connected to a fixed support like this. Here, using extra high tension generator, it produces charge and given to it positive charge. So this positive charge flows onto this. With the help of this brush, this non-conducting belt absorbs this charge like this. And near the brush, it flows onto this plate and resides on the surface like this. If we supply the positive charge continuously to the inner support brush, then it is flowing like this. This brush absorbs the charge and given to this surface. And empty belt moves down here like this. And absorbs the positive charge, moves like this. So continuously, the potential of this outer shell increases. That is the construction and working now. This is connected to X. This EHT means extra high tension, which provides the positive charge. So is it clear now, students?
Yes, sir.
This motor rotates this way, so belt moves upward direction and comes down. Here, this is empty belt. This is positive. This carries positive charge from this brush, and this positive charge is given to this brush. Draw this diagram. This is a collector comb. This is a fixed pulley. Fixed or idler pulley and different down. This is a driven pulley. This drives the belt. This is fixed. This is insulating belt. Insulating belt. From here to here, this is a insulating support. This is a metal sphere. That's why it absorbs the charge. This is a emitter comb. This emits the charge with the help of this extra high tension arrangement that emits the charge to the belt. Okay, ma? By seeing this diagram itself, we can understand. If you want theory, you go through our material, okay?
Yes, sir.
Okay, this is the construction and working of Van de Graaff generator. Okay, ma? With this capacitors, potentials and capacitors are almost all completed, ma? Here some problems are there. Tomorrow we complete those sums and we'll start the current electricity. Amma, is it completed, all of you?
Yes, sir.
Yes.
Okay, Amma. Bye.
Thank you, sir. Bye, sir.
Bye.
Bye.